Recording started. Yeah. Before we start, I'll just feel a few rules about the session. Feel free to ask doubts anytime, and you can stop me in the middle and just ask any questions you have. This is gonna be like a very informal, interactive session. I didn't even get time to prepare slides, so I'm just gonna draw stuff here on this whiteboard and try explaining. Yeah. So let's begin. So before we begin with Kafka, is anyone here already familiar with Kafka or heard about it? If yes, raise your hand. There's this new feature by Google Meets. Okay. So all right. So if not, then no worries. So we'll start with this. So before we can look into Kafka, we'll look into a specific, a particular type of, message passing, a model of message sharing, which is called pub/sub model. So what this means is, let me just move on a bit. Yeah. Okay. Let's say you're working, you are developing a few services, a software, a system, and you, okay, yours, give me a second, people are joining. Yeah. So, and now your system currently, like you've just started it. So your system currently contains two services. One is your front end client, your client, which interacts with your user. So your users are here with and the client is facing them directly. So your users just see whatever the client shows them. And in the back, you will obviously have some database, backend service, right? A backend. Yeah. So to learn Kafka, one is right now you can attend this session. Another, like in the end, I will share a few resources. Yeah. So continuing, you'll have a few backend services. So, and of course, your client will be continuously interacting with your backend service. You could also have, in production, you'll see that a lot of times we want to keep track of what's happening with our clients, right? With the software that we have deployed. So you could have, a logging service which collects all, activity logs on your clients. Now what happens is this client is sending whatever action this user is performing on the client. This client is at the back. It's sending all the logs to this logging service. Right. Let's not worry about what this logging service is doing with the logs, but it is continuously sending the data. There could be another, so this is right now, this is a very simple design, right? You have a backend service, a client, and a separate logging service, which is collecting logs from your client. It could also collect logs from your backend service. So we can make another. Yeah. Now this is a very simple model. Like we don't have to. It's all working fine. Now say this was your web client. Okay. Now you have, suppose you've added one more client, say a mobile app, right? So you have added a mobile client. So we have a mobile client here. And now again, we have users using this mobile client. Under mobile client, you could have an you could have an iOS app and an Android app. So that would be like two different clients. You won't consider them as a single client. And then this also will be, interacting with the backend service and your logging service. So now also, like, our system architecture looks kind of, simple. It's not very complicated. We just have two clients, two different types of clients. And then we have a backend service and logging service. Let's scale it up a bit more. Is there a... Did someone raise a hand or something? Okay. Yeah, let's scale it up a bit more and say we add one more client. You know, anything. Say a tablet client or an Android TV client. Could be anything. Or a console like for PS5 consoles or like different consoles you have clients, right? So you could have another new client here. So console client. And again, it'll interact with your backend service, your logging service. And now say that you have realized that you want to also make sure how your clients are performing on in front of your users, like how fast they are and stuff like that. So you want to collect the metrics to be more formal. So let's have another metrics collection service. And now these clients are going to send their metrics here to this service, right? And your backend service is also, because you want metrics on your backend too, you will have your backend service sending metrics here. Now, if you look at this has become quite complicated, right? Because now this, if you notice, what I'm trying to make you realize is that this kind of system is not scalable. Later, when you add more services at the back here, add more clients here, or any other service, you will have to, these connections, you see these crisscrosses will just increase, and increase the complexity of your system a lot. Why? Because you will think that what's the issue? Like we are just connecting this mobile client to each of the services and making it work. But what happens when say this is all happening through networks, right? Say this is one server, which is the logging service is running, and this goes down. Okay, this logging service goes down, and now you have so this has gone down, and now you have set up another service here, logger, like a temporary one, and the IP has changed. Now you'll have to configure each of these clients to make sure that these clients discover the logging and then shift all these connections here, right? So this is one issue. Another would be just managing so many connections and stuff. This becomes difficult for even for your software, and it even degrades your performance. So what could we do is add an intermediate buffer kind of thing between these services. So something like we have our service A here, service B here, service C here. So these are all our clients, okay? And we have our usual logging service, metric service, a backend service. So yeah, backend service could be anything. And now we add a queue here, a buffer. And let's say, let's call this P. And now what happens is, and let's allocate this for all the, let's make this queue only for all the logs, okay? Let's have one queue for the logs. So now what you got to do is send this here. So all the services need to just write to this thing, this queue. And okay, my bad. So this machine has different queues for logs, metrics, and whatever messages, say events, this backend service is consuming. And now all the clients have to do is write their events or messages, the metrics and logs and the events to this queue, to this machine, and then on the other side, the metric service, the logging service, and our events backend can read from the allocated queues from this machine, right? So now this makes our model much simpler. If you notice, like all the connections are being made to a single place, and even the on the other side in the backend, it's the backend which is constantly polling the queue if there are any new messages from the clients and just pulls them. So if we consider a similar scenario where our logging service goes down, say here, right? What we can do is just start another instance of the logging service and tell it that you have to consume messages from this queue, and it'll start reading. No issues. Yeah, coming to the use cases, yes, I'll come to those after in some time. Yeah, so this is when we move from when our logging service goes down and a new logging service is started. We can just tell that the queue is available here, and the logging service can continue reading from the queue. Yeah. Now, one question that would arise in your mind is like, what happens if this machine goes down, the central queue, right? What happens when this goes down? Now, again, our complexity rises, and we'll have to create a new queue, tell all these machines that the queue is available on this destination, and then shift them here, right? So now this, if you notice, this is what you call a single point of failure, right? We have a single machine which is handling all the queues. And if this goes down, our entire system gets broken. Like there's no connectivity. Clients cannot send data unless a new machine which is hosting these queues available, right? Also, this again won't be scalable because as your clients and backend service rises, like you get a number of services here and a number of clients of whatever any other service here. A single machine, or no matter how powerful it is, won't be able to scale well with this kind of model because it just won't be able to handle the load which is being produced with these multiple machines by these multiple machines. So the model which I talked about, having a queue and making the services write to a queue and the backend services read from there, is called a pub/sub model of messaging. The full form of that is publisher subscribe model. And the name itself tells defines the model. So we have different queues. We can call them topics too, and then there are writers who publish messages to those topics, right? And then there are subscribers which subscribe to specific topics, subscribe to queues and listen for any new data being published there. Whenever new data is published to the topics they're interested in, they pull data from those topics. So yeah, that's why the name publish pops up. Right. Now, Kafka, coming to Kafka, the problem that we discussed here, that this is a single point of failure and the server will go down. So we'll have to, reconfigure our entire system again, and it's not scalable. Kafka solves that a lot, but because if you see the definition, it's a distributed partition and replicated commit log service. So this is a very fancy definition. So we'll break it down. So firstly, the commit log. Commit log is basically your queue. If you can also consider all those messages being written to your a single topic or queue as a commit. You are committing new messages to the topic. So your topic becomes a commit log, right? Now this part, the distributed part, yeah. Now the other part, which is distributed, partition, and replicated, this is more interesting. So earlier we saw that having a single server was an issue for us. It was not scalable and it was a single point of failure. So naturally, what we would do is introduce multiple servers, which somehow coordinate with each other, and provide this service, provide this pub/sub service as a single unit. So that is where your distributed comes in, right? You have distributed the load to different machines. And partitioned and replicated, this is something I'll come, we'll visit when I'm, we're going more into the details of Kafka. This basically, means that it's a very highly available service. So that means that it's very robust. Okay, so whenever you're running a Kafka cluster, you're running multiple servers in it. What could happen is, like, for some unknown reason, a single server goes down, or two, three servers go down in a cluster. So Kafka is made such that it is resilient to these kind of failures, and it can recover from these on its own, right? And how it does those things is by these two terms, replication and partitioning. Yeah, and we'll get into these when we get into details of the core Kafka concepts. Okay. So this was about the definition of, this was about PubSub and the definition of Kafka. Next, someone has asked, like, can you explain any project where you use Kafka? So yeah, there are various, applications of Kafka and even PubSub model. So one could be, as mentioned here. This is actually a real world example where you have multiple clients facing your user, and then even and today this is even more relevant when a lot of places follow a microservices architecture. So what you do is you have your n number of services, and then there are other services which handle your logs and metrics and stuff. And what these services do is push their logs to a Kafka cluster or any other, to be generic here, any PubSub service. And then these logs and metric services pull data from there and process them for further use. Another use case could be, this is highly useful in event-driven systems, right? Say when there you have constructed a pipeline where you have, say, three services. First service pulls some data, processes it, does something, transforms it or something, and then there is another services which picks this transformed data and then works on that. So you could use Kafka or any Kafka here. What you could do is you could whatever data you get, the first service can process it and then publish an event that this has been done, like this the processing has completed. And it can give all the required data about the service, like where the process data is stored and stuff. And the second service can keep on listening to a topic for these events and accordingly start processing the newly processed data. And this can go on in a chain, right? So this is one another example. Yeah. Okay. Let me just erase this off. Now moving on. Now that we know what Kafka is, let's go into some important Kafka concepts. Some the details. So I talked about queues in PubSub, right? The topics. So even in Kafka, the different queues that you have, they're called topics, right? So a topic is a single stream of similar data. Usually that's how you group messages into a single topic. Like say for logs from different services, you make a topic called logs. Okay, so this is one stream, logs. You could have another where you could have events, like we just discussed, like that this process has completed, so the service is waiting on this to be completed, can start now, right? So you can have different topics like these, and then you can have services producing to these topics, and then services reading from these topics. Okay. Yeah, but if you one thing in Kafka, if you remember the definition now, there was a thing called partition, right? So now for us, this, we would think that a topic is like a single unit, a single queue in a Kafka cluster, but it's not. Uh, a topic in Kafka is divided into multiple partitions. So if I take a topic here and zoom into it, it would be something like uh, partition 1, partition 2. So there are multiple queues within that topic. Okay. And they're numbered. Okay. Partition 1, they're called partitions and they're numbered. Yeah. And this is our entire topic. Okay. Yeah, don't mind the bad drawing. Anyways, so this is our one topic, and within that there are partitions. Now, the reason for doing this, why the Kafka designers went with this, is when we look into what Kafka is, it's a distributed system, right? And it needs to be highly available. That means when a client is writing to a topic and another client is expecting messages from a topic, you need to make sure that no matter what happens, like if a machine goes down in your Kafka cluster, the topic is still available. So how Kafka does that is by, instead of having one topic per server, it divides this topic into partitions and puts these partitions on different servers in your cluster. So say if you have if within your Kafka cluster you have 3 servers, right? So what it could do is have partition 1 and 2 on this, and partition 3, 4 here, and partition 0 here. Keep in mind that this is still the same topic. So all these partitions belong to the topic logs, and all of these partitions will be getting messages, which are being pushed by the clients. Though not all partitions won't have the same messages. It'll be different. So when a message is pushed, it enters one of these partitions. Okay, but this ensures that your topic is always available. Okay, and so yeah, so our single smallest unit in Kafka is a partition, and a group of partition forms a topic. Another thing to be note is that the ordering of messages, right? Say I send message 1 to logs and message 2 to logs. The order in which the clients receive them, it's the messages are not ordered in a topic. So the Kafka does not guarantee ordering within a topic. So if I write message 1 to topic and message 2 to topic, it does not guarantee that the client will read message 1 first and message 2 first. And that is quite obvious when you see that there are different partitions. As I said that, when you write a message, it can go to one of these partitions. So say when you wrote message 1, probably it went to partition 0. And when you wrote message 2, it went to partition 2. And when a client is consuming, they also can consume from one of these partitions. Okay, it's not like they only read from one partition. We'll come to that more, but yeah, they can read from any of these partitions, right? Parallelly. So say our client reads from partition 2 first. So they get message 2 first, and then they read from partition 0, so they get message 1. So that's why ordering is not guaranteed in Kafka topics. But if you look into this, at what level do you think the ordering is guaranteed? Any guesses? Okay, it's quite simple. If you look at the way I describe this, if both the messages were pushed into the first part, the partition 0, right? So if message 1 was sent here and message 2 was sent here, then when a client is consuming from partition 0, it is guaranteed that you'll get message 1 first and then message 2. So ordering is guaranteed at partition level and not topic level. Uh, is everything clear till this point? Like, let me know, because after this it'll just get more complicated. All right. Okay. So now this was about topics and partitions. One more thing about partitions is that the third word in the definition, replicated. So, replication is one thing which is performed in most of the distributed system, just to make sure that your data is highly available, right? If some important piece of data is just kept on one machine and that machine goes down, you lose that data. So you replicate it. And the same thing is done here. Your Kafka replicates your partitions. So when you have partition 0 here, uh, probably these three services are in a Kafka cluster. Okay, probably this partition 0 is also being a copy of this partition 0 is being maintained here too. Okay, it could be maintained here too, and similarly, for partition 1 also some copies will be maintained. What this ensures is that, say, when some server containing your main Kafka server containing partition 0 goes down, another server which was maintaining a copy of partition 0 can continue serving requests for partition 0, till this server comes back. I mean, there'll be no loss, right? So that is what the replicated part means. All right. Yeah, so this was about topics and partitions. Yeah. Moving on. Another important thing to know is that in Kafka, there's no, it's the other way around. Messages in a topic are unordered, like they don't guarantee ordering. But when you send a message to a particular partition, within a partition, they are guaranteed to be ordered. So, say if I sent message 1 and message 2 to topic A, it won't guarantee that you will read the message in the same order. Okay, so you won't get. It's not guaranteed that you get message 1 first and message 2 first. But if I wrote them to the same partition, say message 1 it goes to partition 0, and message 2 also goes to partition 0, then I'm guaranteed that when I'm reading from partition 0, I'll get message 1 first and message 2 first. Does that clear your doubt? Okay. Yeah. Okay. So continuing, yeah, I was going to say there's nothing about schema of the message, like what you send in your message, right? So for the sake of simplicity, right now, let's just say that you just send, let's not get into the structure of a message right now, but say the messages you send, there's no particular schema that you need to follow for the message payload itself. Kafka does not, have any restrictions on that. It just deals with that will come to it, like which partition it's supposed to go. We can specify that actually. So yeah, when we deal with producers, I'll explain that. Okay, so Kafka just deals with chunks of bytes. Okay, whatever is the message is just a chunk of binary digits for it. It does not care like what you have stored in it and how you stored it. So you could probably have a JSON and then binary encode it and send it as a chunk of bytes, and Kafka won't care. So why this is important to know is that usually when you are building applications, you want your different messages to have a specific schema defined, right? It's a good practice to have a defined schema for different messages you send, because then all the different people who are talking to each other will know what the message means. If there's no particular schema, it'll just be chaos. So it's up to the clients, which will come to like who write and read from Kafka to properly serialize and deserialize the messages being sent into the required format. Yeah. So coming to the clients. So clients for Kafka are named, there are two types. There are producers, there are consumers. So the name itself suggests what these two are. Producers write to a Kafka topic. So these are producers. Okay. And consumers read from Kafka clusters, right? They read from a topic. All right. Now these producers and consumers, there are a lot of configurations available. There are different ways to write, and it's there are a lot of things which are undergo within these producer and consumer clients themselves. So we'll go into these one by one. So let's start with producers. Okay. So on a very simple level, you could just think that a producer, say P, say it wants to write to a Kafka cluster, right? So I want people to make guesses here that it needs to write a message. What all things do you think we need to specify to make this producer run properly? And there's a Kafka cluster here. I'll wait for like 30 seconds or so for people to make guesses. It's totally fine if you make there's nothing right or wrong here. So yeah, true. So as Ishan just said, you would need to know what topic you need to write to, right? Because we saw that there are different queues in a Kafka cluster, right, which are called topics. So you'll need to know the topic that you want to write to. Okay. Then the other thing will be the message itself. You can't send anything if you don't know what the message is, or the message and the partition. Okay. So yeah, this is where the load balancing thing comes in. Comes into picture. So as a producer, you have an option to specify which partition within the topic you want to write to, right? So partitions within a topic are just numbers. Their names are numbers, so 0, 1, 2, 3, like that. So you can specify the partition number which you want to write to. Okay. So if you don't want to, if you are some what you could do is, in a hacky way, that you want ordering properly, you could just write to all messages for this topic. You could just send to the partition 0, right? Now what would happen is that Kafka, because you have specified the partition, it'll just go to the partition 0 and your messages will be ordered. But this does not always, this does not how do I say, make use of all the features that Kafka provides, like its distributed replication and stuff. And the main use of partition is load balancing, right? So when you are writing to a single partition all the time, you're just going to increase the load on the server which has that partition. Only that server is going to be used to serve all the requests, right? Because that server is handling that partition. But if you don't specify a partition and just write to a topic, yeah. So coming to that case, when you don't specify a partition, what happens is within a producer there are different components. And when I tell components, these are basically producer clients are basically libraries provided by the makers of Kafka themselves, which handle a lot of these things like load balancing stuff internally. And they expose an API to send messages and stuff, right? So all you have to do is create a payload which will contain your message and your topic T, and optionally a partition. So optionally a partition, right? And there's one more thing which I forgot to tell, is an optional key. Okay, this too is optional. All right. Now, if we move down, What happens is within the client library of a producer, when you create this and put, say that I want to send it internally, first thing that happens, it goes to this partition resolver. I think that's what it's called. I don't remember the exact name. So what this does is it checks if the message has any partition specified. If it is specified, it'll just send it to that partition. Okay. If it is not specified, it does one more thing. It takes the key, it creates a hash of the key, and this hash is internal to this is the hashing algorithm they have implemented in the library itself. It's common to all Kafka clients, and it creates a hash, and depending on the hash, it decides which partition it should go to. Okay, and it is done in such a way that the messages are equally load balanced along amongst the present the available partitions. So why this is done is to ensure that say you have a message with a particular key, right? It is used to ensure that messages with a particular key always go to the same partition, so that whenever the message is repeated, you can expect it to go to that same partition, because the hash will always be the same, right? uh, if people don't know what a hash means, I can explain. Anyone who has any doubts regarding what a hash is? All right. So now, but yeah. So depending on the key, it decides which partition it's supposed to go to. If the key is not specified, then it just selects one of the partitions in a round robin fashion, and that is how messages are load balanced amongst different partitions, right? So once that is done, it takes the message, decides which partition it should go in. Now also they're not sent, actually they're not directly sent. What it does is it maintains buffers internally, okay, the client library itself, on the client side, and these buffers are per partition. So this is for partition 1, this is for partition 2, this is for partition 3. Say we have 3 partitions right now, okay, and say this is message 1, okay, and we decided that it goes to partition P1. So it'll just push it in the queue here, right? Same. So you could have many messages here stacked up, and you could have messages stacked up here, and it waits for some time for this queue to be filled. I mean, not entirely, but some to some extent. And when these messages are grouped together, it pushes them in a batch. Okay, so now say like some threshold has reached for this P1 buffer. So what it does is, so all these messages together, it'll group them and push them in a batch to the Kafka servers, Kafka cluster here. Okay, this is when it sends them. Actually, like it makes the till here. This is the boundary of the client. Till here, everything is happening on the client side itself. Yeah. All right. So and once this is done, like the batching is done, it sends it to Kafka. So why this is done is to reduce network congestion, the load on a network itself, right? Say you were sending messages as soon as they were produced, so there was no buffering or caching here. All you would do is, as soon as a message is produced and you decide the partition, you just send it to Kafka cluster. Now, if you're producing 10, 20 messages, that is fine. 10, 20 messages in a minute. But think of cases when you're producing like millions and billions of messages per minute. You'll be creating a connection again and again to send the message, right? And that just won't be good for the network. So instead, what you can do is just send them in chunks, in batches, and make sure the network load does not just increase. Yeah. So this is on the producer side, right? So any doubts on how a producer works? Also, one more thing that I forgot was before you can start producing messages, you need to tell the producer where the Kafka cluster is available, right? So you also, before starting the producer, you need to tell it, before writing a message, you need to tell it a few IPs or some, not IPs, like some DNS names, basically locations where your Kafka servers are available. Say you have like 5 servers in your Kafka cluster. You don't need to tell all of those 5 server locations. You can tell like 2 server locations or something. Two, because say one server is down, so it can contact the other. And once it contacts them, the servers it'll automatically find out what all topics are available, how many partitions are there for the topics that it needs to write to. The servers tell the producer, and it's all negotiated. What happens if a partition is full? Okay. Okay. Oh yeah. So one very important thing that I forgot to mention, that your partitions, they can't really, theoretically they can't get full. So how Kafka stores your messages is that it writes them to a disk. That's why it is persistent. Okay. So you won't lose the data from your disk if the server goes down. It'll still be there in a disk, though the service won't be available. So when it gets the message, when the Kafka server gets these messages, it's maintaining a few files. Files that it maintains are per partition wise. Okay, so this is topic T with partition P1. So this is a file, and TP2. And whatever message it gets for partition 1, say these 3 messages, it'll just append it to these files. Okay, and these are being stored on disk. Now, say the server runs out of memory, right, and it's not able to write. So what will happen in this case is this will be detected by other servers in the cluster, and they will automatically switch to a different leader. So they'll consider this cluster which has run out of memory to be down. Okay, that this server is down, so it's no more usable. And because of all the replication and partitioning, Kafka the cluster will automatically recover from this. Does that make sense? But in the case when all the servers are done, the memory is full, then you can't do anything. Like, you will have to scale up. That time the server will just return an error. So what happens is, once the producer client sends the messages in a batch, it waits for an acknowledgement from the server. So it waits for an acknowledgement from the server saying that I have written all the messages properly to the disk. I've written all the messages, I've received them. So in this acknowledgement, if for some reason it couldn't be written, there are a lot of reasons why it won't happen. Like, one possibility is that this topic doesn't exist at all, or this partition does not exist. Like, the producer client made a wrong request, or say the server is down, and it's full, or it's filled, like there's no space. It'll just say that there was an error writing the message. So you'll know that the message couldn't be successfully written. Does that clear your doubt? All right. Okay. So moving on, there are coming to ACKs. This I mentioned. There are different ways you can write to a Kafka cluster. Okay, depending on the different use cases you have. So let's go back to some of the use cases that we discussed earlier. One could be collecting different actions being performed by users on your client, right? Say your website, and the client is clicking these buttons and stuff, and moving the mouse pointer here and there, and you're collecting those events and sending it to your backend services. So this could be one type of use case, right? That your producer will be running in your web client, and will be sending messages to your Kafka cluster. Another type of use case could be your monetary transactions, like your debit card transaction and stuff. when say you swipe your debit card, enter your PIN and stuff, and create a transaction, and these transactions are being collected in a Kafka cluster, and then some the processing service which processes the transaction and confirms that it was successful is reading from this Kafka cluster. Now these two use cases are quite different from each other. Okay, in the first use case, where we were collecting user logs, data loss is not a huge problem for us. Okay, because say I am clicking 10 times on like 10 different buttons, and if I lose one click, one message in that, it's not an issue for us. It's not a big deal because it's just we're just collecting user activity and trying to predict something. Yeah, so losing that click usually won't matter a lot to you. But in the other case, in the transaction case, losing a transaction will affect your service a lot. Say you're continuously losing transaction, then you'll start losing your customers too, because they'll think that this service is not reliable, right? So that is one thing. Another thing could be ordering of messages, right? While I said that within a partition, messages are guaranteed to be ordered. This is a very distributed environment. This is a distributed environment, right? You have your producer running somewhere on the other side of the network. It's connected through a network to the Kafka cluster, and then you have your clients reading from it, right? So what could happen is, due to some issues in the network, say I click the first button for like button A first and then button B next. Okay, even though the client sent the events in those orders, due to some issues in the network, the Kafka cluster could receive them in a different order, right? And what could happen is, it gets the message second first in the partition, message for message A later, and now the order is reversed. Now this is not a huge issue again in our user activity case, where we are just tracking the clicks and mouse movements and stuff. But it becomes very important in our transaction cases, because collecting, say, getting 100 rupees first and then spending 100 rupees is quite different from spending 100 rupees first and then getting 100 rupees. You can't have a negative balance in your account. And so if you have 0 rupees in your account and there is a transaction which says that now you're spending 100, the processing service will just deny it, saying that you don't have enough balance. Though on the client side, you actually performed it in the right order. You first added 100 rupees and then spent 100 rupees. So depending on different use cases, Kafka provides you different configurations for your producers and your clusters to write messages to the cluster. So one way to configure your cluster, your producer, to make sure that you are writing all the messages to it, is to write synchronously. Okay, so what you can do is, your Kafka cluster is here, your producer is here, and you send one message, message one, and then as I told, it sends the ACK, right? So instead of sending it in batches, also you can just send one single message per batch, and wait for an acknowledgement that you have received the that the message has been written. Even if you send in a batch, send it in a batch, because it'll be a single unit which is being sent across the network. It won't be an issue, and within the batch, the messages will be ordered in the way they were sent. Okay, so after you send a single batch, you wait for an acknowledgement that the messages have been committed to the partition, and then you send the next batch of requests. Okay, so this is like a synchronous manner in which you write to the partition, the topics, and this ensures ordering, and it also ensures that there was no failure, right? Because you're waiting for your you're waiting for your messages to be committed to the partition before you are sending the next set of transactions. So this would be very useful in this case, right? But in this case, this will just be a degradation in your performance, because waiting for a batch to be sent and then sending the next one is just slowing down your it's just reducing your throughput. Uh, and in the case of user activity, you don't want that, right? You don't care if you lose messages, it's fine, but you just want it to be done as fast as possible, because there'll be a lot of events being generated. So you can write asynchronously also. Actually, there is asynchronous, and there's one more which is fire and forget. So in fire and forget, what happens is you just fire this batch of messages to the Kafka cluster. You just send it to the Kafka cluster, and you don't care about the ACK. Okay, you just keep sending to it, and you don't care whether what the Kafka cluster is saying to you. This is not This is usually not used a lot. The other alternative for this, because even if it's user activity, you want to know whether the message was written or not, so that you can perform a different action if you realize that a lot of messages are not being written. So there's an asynchronous type of writing. In what you do in that is you specify a callback to your producer, like a function which needs to be called whenever you get an ACK for a batch. Okay. And what you do is you send a batch, and you don't wait for the ACK. You process and send the next batch. And when you get the acknowledgement, the producer client calls the callback function that you specified. And in that callback function, you can perform whatever relevant actions you need to, depending on what kind of acknowledgement you want. Right. So this was there. A lot of other things are there within the producer which are quite a bit complicated, and we won't get into it here right now. But yeah, this was like a very an overview of producers in Kafka. So is everything clear till now? Any questions? Say yes, so that we can move on to the next section. Okay, I see a couple of faces. So yeah, I'll just remove all this. All right. So now that we are done with producers, the next thing would obviously be consumers, right? Now, consumers are the clients that read from your Kafka topics. So you have a Kafka topic here. Okay, is there? Okay. You have a Kafka topic here, and you have a consumer here, and it reads from a Kafka topic. So again, obviously, you can guess what all information you need to read from a Kafka cluster. You need to know the location of the cluster, like location of a few servers in the cluster. Then you need the topic you want to read from. Okay. Anything else that you think will be needed? All right. Okay. Yeah. So you don't need anything else actually. There's no message component here and no key component here, because yeah, we are consuming messages. Now, one important concept within consumers is a consumer group. Okay. We saw in case of producer, we just have a producer which produces to the Kafka cluster. But in case of consumers, there's an option called consumer groups. What that means is you can have a group of multiple consumers, C1, C2, C3, C4, okay, which are doing, say these four consumers are working for the same service, say metric service, okay. So they are all reading from the metric topic. So this is the metric topic, okay, right. But because they are in the same, the same topic, what happens is the different partition that this topic has, right? Like say it has 6 partitions, okay? So there are 6 partitions in this topic. 1, 2, 3, 4, 5, 6. Okay. So what happens is that each of these consumers reads from, like, a single partition can only be read by one single consumer. Okay, so it's like the mapping is made that one partition is mapped to a single consumer only. So say the first partition is being read by consumer one, even the second partition is being read by consumer one, then the next partition by consumer two, next by consumer three, next by consumer four, and the last partition also by consumer four. Okay. So yeah, you can have a distribution like this. Is this clear? Like how how I made this distribution? Any doubts? So basically, a single partition is mapped to a single consumer, but a single consumer can be mapped to multiple partitions. Yeah, within a consumer group, that is. Okay. All right. Now, why this is done, okay, and why it's not done for producers? Like, why is there no such thing as producer groups? Uh, a reason for that is that when you're producing messages, you don't really need, different producers to coordinate with each other to which partition they are writing when they're producing messages, because the different messages that they're producing are kind of exclusive, right? That it's a new message it's a totally new message. But so there's no issue, right? Uh, and you can easily have a lot of producers producing to a single topic. But on the consumer side, you need some kind of coordination. Say you have one consumer C1, okay, and there's no such thing as consumer group, and it is reading from the metrics topic, okay. Now, when there are a lot of producers writing this topic, you will definitely get the need to scale your consumers up and launch another consumer so that it can process the data faster. Otherwise, your pipeline will slow down, right? So say you start another consumer C2. Okay. Now what can happen is, say, yeah. So what can happen is that, say, C1 reads from partition 0, and now even C2, because it's running, say it also reads the same message from partition 0. Now I hope you're getting the issue, right? So both of these may process the same message again, which is not needed because they are working for the same cause. Like, we just scaled it up, so we want them to work on different messages from the same topic. So that's why we group them in the consumer group and say that like consumer one can read from a certain group, bunch of topics, and C2 can read from the remaining partitions, not topics, sorry, partitions. Yeah. Yeah. Does that make sense? Okay. I'll assume that makes sense. One important thing that I forgot to mention earlier, which was very important in the partitions, was that how the messages are stored in partition. Okay. So say you have a topic, and within that you have partition. So when you push a message, it gets a number which is called the offset. Okay, it's basically a serial number for the message. So the first message in the partition, say it could be, the serial number could be 0. Then you could have 1. Then you could have 2. You could have 3, right, and so on. Same thing here. The offset here would be 0. It does not always have to start with 0, like that. But say that we have started the cluster now, and the message these are the first messages for the partition. So these are the offsets. So these message numbers are called offsets. Okay, offsets because and within, say, when how do you know what is the starting point? Right now we have assumed 0, but internally Kafka clusters, the servers, they maintain something called a low watermark. Okay, low watermark. This is basically the start of the message lines, and they also contain a high watermark, which is basically the number which is the latest message present in the partition. Now this low watermark can move forward. Okay, it does not have to start from zero. It can be here also. When this will happen, so this can happen when your messages are deleted. So Kafka does not persist your messages forever. Okay, there is a limit to like these many for these many days. Like you can specify the time. After that, it'll just remove that message. So your low water mark moves forward. Okay, so basically this is the oldest commit, the oldest offset you have inside your cluster in your partitions. So say your limit is 10 hours. So after 10 hours, like when this message zero message becomes 10 hours old, the low water mark will move forward like that. There's one more thing called commit offset, which is specific to every consumer, okay, or a consumer group. Uh, it's actually so what that is basically the latest offset which was read by the consumer. So say there's C1 and it last read the offset 2 rate. So this is the commit offset of C1. Okay, so commit offset. So it basically tells you the last message read by by a particular consumer. This is different for different consumers, but in a consumer group, it is same for all the consumers. Okay, so the commit offset. Say you have 4 consumers in a consumer group, the commit offsets will be common for all these. So now instead of belonging to a particular consumer, this commit offset will belong to a consumer group. Okay, so what this does is it makes sure that the different consumers are not rereading the messages. The commit offsets are common for all of them, right? So it's basically a single unit, which is internally they're dividing their work at a different level. Yeah. Uh, this was, I forgot to mention it earlier when I was explaining partitions and topics, but yeah, was this too confusing? I can go over this again. Does this make sense? Uh, any replies? Okay, yeah. So sure. So a commit offset basically. Let me erase this. So a commit offset specifies say you have a consumer C1, so and you have a consumer C2, okay, and these are totally different. Okay, they're reading from the same topic, but they are reading the messages and doing 2 separate things. Okay, this is probably reading the messages and storing them in a database, and this is probably processing the messages and sending it further somewhere else, right? And now say consumer 1 has read all the messages in the queue till the first 3 messages. Okay, so 0 1 2 consumer 1 has read, right? So now when next it requests for a message, it needs to know like from where it needs to start reading, right? It does not you do not want it to read the messages 0 1 and 2 again. You want it to get the third message, right? So how that is done is that for the consumer, there's something called a commit offset, and it is stored in the Kafka cluster itself in the servers, which tells the server like how many messages it has read till now from the topic, from the particular partition actually. So for this partition, so C1 had read till the first 3 messages. So the commit offset of C1 will be at 2 commit offset. Okay. Yeah. So next, when it requests for more messages, it tries to read more messages from the topic and this particular partition. The Kafka server will know that it has read the first two messages, and the new message that it needs to send to consumer one is the third message. Okay, but say now consumer C2 is also reading from the same partition and from the same topic, and from the same partition also. Like I'll be interchanging topics and partitions now, because now that we know how they work, right? Yeah. So now this is also reading from the partition, and it's a totally different thing from this consumer one, right? And say it has read only the first message. So now for this consumer, the Kafka server needs to know which message to send next, right? Which will be message one and further message two, message three. So it stores an offset for consumer two over here. That, like, this is the last message that consumer C2 read. Okay. So whenever C2 requests for more messages next time, it will send one, two, and three. Or further, right? So it'll send them in that order. So why this is done is why there are different commit offsets for different consumers is obvious, because two different consumer doing two different things on the same messages does it. They always won't be at the same message all the time. Like, so one consumer, maybe I had reading, maybe it read more messages than the other consumer, like in this case. The Kafka server stores the latest message that it read, a particular consumer read, right? So this is one case. But what happens in a consumer group is that, like, you make a consumer group when all the consumers are doing a similar task. They're doing the same task. Actually, like, say processing is taking too much time. You notice that if this single consumer is reading messages very slowly. Like, you saw C1 that it read 3, but C2 was still stuck at 0, right? You can add more consumers and create a consumer group. So you can add 2 more consumers and create a consumer group. And what will happen is that, and you'll have more partitions. Actually, this is like a single partition, but you'll have more partitions. Now, what will happen is that these consumers will start reading from the different partitions, right? So probably this is reading from this partition, this is reading from this partition, and so on. And now this commit offset that is stored will refer to the entire group, not just this C2 consumer. So say maybe later this C2 goes down, right? And now this partition is assigned to this second consumer in the group, right? So the commit offset, which was set for this C2, was actually set for the entire group. Okay. So this new consumer, this consumer which was assigned this partition again after this went down, will start reading. Will continue from the commit offset which was last read by C2. Okay. Is it clear now? It is a bit confusing, I know. That's why I. All right. So yeah, so by having consumer groups, you can divide the load between different different units, and process the entire data faster. Now coming to how consumer groups work and how partitions are assigned. So in a Kafka cluster, where you have different servers. Okay. So you have, say, 5 servers in your Kafka cluster. And you create a new consumer group containing 3. You create a CG consumer group containing 3 consumers. Wow, it became a no. Okay. Yeah. And you have a topic P1 in this Kafka cluster with 5 partitions. 1, 2, 1, 2, 3, Four. Okay, take four partitions, not an issue. Uh, Four partitions. So now how these partitions are divided between the three consumers is that for every when you create a consumer group, the cluster allocates a group coordinator. Okay, it's a server which basically coordinates all the functionality, administrative functionalities for a consumer group. So when I create this consumer group, and say the in the cluster by voting, say this server is picked as the coordinator of the consumer group. Okay, for this consumer group. Now, what this coordinator does is it first picks a consumer leader. Okay, from the consumer group, it picks a group leader. How it does that is very simple. Like it basically picks the first consumer which joined the group. Okay, so say C1 joined the consumer group first, so it assigns C1 as a leader. Okay, and now this consumer group wants to read from topic T1. Okay, so what happens is for the topic T1, the group coordinators in the Kafka cluster, it will send how many partitions are available. So 1, 2, 3, 4. There are 4 partitions available. It will send how many consumers are currently present in the consumer group. So there are 4 partitions and 3 consumers in the consumer group. Okay. So now that this is done, we it will take this information and send it to the group leader, which is C1 in our case. So C1 will get this information and it will divide these 4 partitions amongst the 3 consumers. Okay, so say it will say that I will read 0 and 1, and C2 can read from 2, and C3 can read from 3. It will say this and send a reply back to the coordinator, which is the server here. And this coordinator, once it gets the list, it will send the partitions for the topic T1 assigned to each consumer. So C2 will get to know which partitions it is supposed to read from, but it'll never get to know what partition C3 is reading from. That information is only stored with the leader, which is C1. Okay, because it assigned all those things. So yeah, this is how the distribution is made. Now, what happens when a consumer leaves the group? Say C2 went down or somehow it leaves the group. Okay. What happens now is the group controller detects that C2 went down and it immediately pauses all read operations from topic T1. It tells the for this consumer group, okay, for this particular, not for all consumer groups, only for this consumer group, because this group controller can only control this particular consumer group. Say the consumer group name is A. It'll tell that you can't read till you rebalance the partitions. So now what it does is again sends the list of partitions and a list of consumers to C1. C1 will repeat the whole process again with the new data and assign the partitions, and the whole operation will resume. Okay. What happens when the group leader itself goes down? It will elect a new leader and then do the same thing, and rebalance all the partitions. How it detects that the consumer is live or not is very simple. All the consumers they send a heartbeat to the group controller. Okay, every 10 seconds. You can configure this in the consumer library in the client. But say every 10 seconds, the group controller expects a heartbeat from each of the consumers in the consumer group. If it does not receive that heartbeat, which is basically a single ping, okay, like you can say ping group controller, and that's it. something like that. It pings them to let the controller know that I'm alive. So C1 will ping the group controller every 10 seconds to let the controller know that I'm alive. Okay, this keeps on happening. If this is then easy. Like the group controller knows all is well and everyone's alive, and yeah, the operations are happening without any issue. But say C1 does not send a heartbeat for for some time. So now the group controller will assume that C1 is dead and will initiate a rebalance. And that is basically the whole process of stopping reads, then reassigning the partitions to the remaining consumers and stuff like that. Yeah, so this was about the consumer groups. Yeah, and how the partitions are assigned. If was this clear? Okay. If no doubts, then we are like reaching like the last part of this, which is the Kafka, the cluster itself. We talked about producers and clients, but we didn't talk about how the cluster itself works internally and gives a very highly available service. So yeah. Coming to the Kafka cluster, till now I've been calling each of these services in a cluster as a server itself. But in Kafka terminology, every server in a cluster is called a broker. Okay, it's a broker. So there can be multiple brokers because it has to be a distributed system. So no point in having a single broker. One good thing when you're deploying a Kafka, deploying a Kafka cluster is to have odd number of brokers instead of so something like 3, 5, and 7, because how the leader of different, because a lot of voting happens for different purposes, and in that case majority vote is taken, right? And for that it's good to have an odd number of servers. So yeah, so say you have 5 brokers in your Kafka cluster, right? So every Kafka cluster has something called a controller. Okay, the cluster controller. This is like the leader of the whole of the whole cluster, and performs administrative tasks for various administrative tasks which are there. One thing, like how this controller is decided is that uh, Kafka use for storing all its configuration and stuff, like who the controller is, what all topics are there, and what partitions are there. It uses Zookeeper. Okay. Now Zookeeper is another service provided by under Apache, which is usually used for storing configurations and stuff. Okay. Uh, and it stores all its configuration in Zookeeper. Okay. Now, when you create a new cluster and the first server joins the cluster, in the Zookeeper configuration, it registers itself as the leader, okay, the leader of the cluster. So it contacts the Zookeeper server and tells that I am going to be the leader. Every server which joins the cluster also does that, okay? It says that I'm going to be the leader. But what happens is, because the first time this broker joined and says that I'm going to be a leader, Zookeeper says okay, and the next the other servers which try to join and say that I want to be the leader, Zookeeper says that there's already a leader, so I you can't be the leader now. So and yeah, so that's how the leader is decided. But at the same time, what happens is Zookeeper tells them that I'll let you know if there are any changes in this configuration. Okay. So what happens after this is that once you have the controller assigned, so say this became the controller, and you have your Kafka cluster here. Yeah, so this is the controller. The first thing you want to do is for all the topics, say you have a topic T1, okay. So you want to assign the different partitions of the topic. I said that you can have different partitions. So 4 partitions, 4, 3, 2, 1. Okay. You have 4 partitions, and the first thing it'll do is it'll tell which brokers are supposed to have which partition of the topic. So it'll assign, say, partition 4 to this broker. Okay, so this has P4 and P3 here, P2 and P1 to itself. Okay. It'll also tell which all servers are supposed to maintain the replicas of the partitions. As I said, the partitions are replicated. So it'll say that this broker is supposed to maintain a replica of P32. This is supposed to maintain a replica of P1 and P2, and so on. Okay. You can specify when you're creating a topic that how many replicas should be there for each partition. Okay. You can specify how many partitions should be there, and you can specify how many replicas for the partition should be there. After it tells which all after like it's decided like which all partitions are to be there, and where they're supposed to be and where the replicas are supposed to be, it picks the lead for the partition. Okay, so say you have partition 4. Now partition 4 is available here, and say it's available here too. Right, they are maintaining copies. So it decides who is going to be the leader for this partition. Say this is going to be the leader, okay, this server. Now once it's decided that this broker is going to be the leader for partition 4, all requests, suppose a producer is trying to produce to the topic T1 and it's sending the message to partition P4, okay, this request that is sent is supposed to go to this broker. Okay, the producer, if it sends this request to a different broker, say it sends it to this broker, and this broker does not even have partition P4, the broker will return an error. Okay, it'll say that I don't have the permission to serve the request for this partition. Suppose if this producer requests a write to the partition P4 from this broker, which has the partition P4, it still say that it can't write to this partition because it is not a lead. It is not a leader. Okay, it is not the leader for this partition. The leader is this one. So it'll again send an error. So the producer will have to send this message to this broker itself. Okay, so this is one point. Even for a consumer, say the consumer wants to read from topic T1 partition 4. Okay, if it requests this, if it sends this request to this broker which does not have P4, it'll get an error. If it sends this request to the replica, it still get an error. So it only can request for the messages for partition P4 of T1 from the lead partition. So all requests pertaining to a particular partition can only go through the lead, can only be done through the lead partition, the server which leads the partition. Other servers which are just replicas, they just fetch data being written to P4 and then put it in their replica. Okay, so this simplifies your entire process. Now you'll be wondering how to know how does the producer and consumer know which broker is the leader for the particular partition. If we had to do it manually, it'll be a big headache. So we don't have to do it manually. Each of these brokers maintain a cache of the metadata, like this partition in this topic, this is the leader, how many replicas are there, which all servers have the replica. All that metadata is stored in a cache on each of these brokers, and the producers and consumers can make a request for the metadata. Okay, and before starting their operations, they always make a request for this metadata and cache it in their buffers. Okay, cache it in their memory and decide which server they need to make the request to. All right. So using the metadata, they'll know that I have to. The producer will know that I have to send the data to this broker itself for partition P4, and the consumer will know that for partition P4, I'll have to contact this broker. So this is simple, right? What happens if the leader goes down? So this broker has gone down. The producers and clients, the consumers can't do anything now. Right? They'll be trying to contact and it's gone down. Now it's the job of the controller to assign a new, leader for the partition. So when this broker goes down, the controller will realize that again by heartbeats. I think, yeah, so he'll realize that this has gone down. Actually, I don't think it's heartbeats, it's by Zookeeper. I'm not sure about that. But yeah, he'll realize that this broker has gone down, and then he'll compute, how many partitions need a new leader, because it is not necessary that this broker was the leader of only this partition. It could be that this broker was the leader of all these partitions, though that usually does not happen. But it could be possible that for another topic T2, it this broker was leader for one of the partitions of T2. So it computes what all partition need a new leader, and then it also computes how many what all brokers had a replica of the partitions that require a new leader. And once it knows like this broker has a replica of P4, it was maintaining a replica of P4, so it says that this you can be the new leader, so this becomes the new leader of partition P4, and the metadata is updated in all of these brokers. So now producers and the consumers will request for metadata. They'll know that this is the new leader for the partition, and they'll start sending requests to this guy over here. Yeah. So this is the failover the recovery mechanism that I was talking about in distributed systems, right? We saw that initially when we started with a single queue in PubSub, if the server goes down, we have to reconfigure our entire service. But in this case, what happens, like when one server goes down, automatically all the messages were being saved somewhere else. The cluster itself recovers from it automatically, and even the clients and producers realize that the location has changed and they have to contact another server, and it reduces a lot of it remove work for us, the developers who are writing services for using these services. We don't really have to worry about these internals of switching from one server to another and stuff like that, right? uh, did this process make sense? Okay. Yeah. So apart from this, so we have covered partition leaders, controllers, and brokers. All right. One final thing that I wanted to mention was, yeah. So I think we're done with like most of the concepts of Kafka, like at least the things that I wanted to discuss. Uh, Now, just we'll just give. I'll just discuss about some use cases of how Kafka is used usually, right? There is something in production and in by different various industries. So usually right now, there's something coming up called stream processing. Okay, and Kafka is like in the center of that right now, as far as I know. So that stream processing is basically, you can consider a Kafka topic to be a continuous stream of data, right? Producers are producing, consumers are consuming, and this is a stream of data. So stream processing is basically a term given to processing on the go and in the streams, and these stream processors which perform stream processing are basically a high level version of producers and consumers. So what happens is, say you have data flowing in topic T1, and then you could have like and it's in a particular format. Okay, so say it's like in a given schema, like A is this and B something this. Okay. Now what you can have is you can have a service here which consumes data from this stream, and it computes it converts this data into something else. It can say you create something like sum is a plus b, which is 3. Okay, and it puts it into a new stream t2, which contains all the sums. Okay, so it consumes from this stream and pushes to the stream. So you're basically converting data, okay, within the stream itself, and this is something this is called like stream processing. And this was a very simple example, but there are a lot of use cases of this. One case that which, if people in web club who attended the Netflix system design would know that in Netflix, it follows microservices architecture. All right. So you have millions of services talking with each other, and for they need to know like how how the services are talking with each other, and what just to make sure, just to know that everything is working fine. They maintain a log and graph, kind of like a graph of all the communication happening. So how this is done is, say service A. I'm giving a very simple example. I'm, I'm making it very simple. It might not be exactly how they're doing it right now, but say service A is sending a message to service B in the right. So it creates a log. That log is created that they use AWS, right? So in AWS, there are different services to keep track of what is happening in the network. So AWS creates a log that a message was sent from IP of, say, the IP of this is x.x.x. We'll just say x, and the IP of this is y. So we'll say that a message was sent from IPX and this port to IPY and this port. Okay. Yeah. So this is fine. Now this is the logs we are getting. Okay, from AWS, and they are being produced like in a stream. Say, just assume that they're being produced in a stream. So you can push this into a Kafka stream. Okay, in a topic. But if you realize that there are millions of services, okay, in the system, so what? Yeah, just don't bother about the number. But okay, say there are millions of services. So these IPs won't really make sense to a normal user like you and me, uh, who's debugging the entire system and trying to find out what the issue is, right? Say there is an issue with service A, and these IPs won't really tell you anything. Another issue will be that these services are not bound to this IPX. Okay, it's a distributed system, right? So what could happen is that right now the service is running on an IPX. For some reason, this say it's running in a container, and the container goes down. So this service is brought up again in another container, and it'll have a new IP Z, right? So this kind of data, like IPX is sending some request to IPY. These kind of logs are not really useful to the people who are debugging the network and trying to find out the issue. So what they did was that they created another stream of data which tells you that the IPX was assigned to this service. Okay, say service A. Okay, this is another stream in topic T2. And then there is a stream processor which consumes data from both these streams. And depending on the messages from T2, it knows that this IP belongs to which service, right? Say later when IP, the container with IP X went down and service A is brought up in with another IP Z in another container. So there'll be another message, right? with exchange change to Z. Like basically all the changes happening to the IPs and the services, right? I mean, sorry, the message format is wrong. So ZIP was assigned to service A. So this is one stream. This is another stream which is telling which IP sent a request to this IP. Now this stream processor combines these two streams and gives out another stream in the format service A sent some request, and it gives a lot more information, but I'm simplifying it here. Sent a request to service B, right? And now this is way more useful for us. Okay, now we know like the whole trace of the entire network, like how the different services are communicating with each other, and we can find out what the issue is, like which service is causing the issue in the system. uh, was this example clear? Another very simple use case could be just you could have logging, a metrics database or something like Elasticsearch. Usually, a search, for logging and metrics. Usually, you store it in Elasticsearch or something, which in where you can index these metrics and perform analysis using Kibana or Grafana or stuff like that. So you could have your ELK here, Elasticsearch database here, metrics and logs. Okay, and you have like thousands of services creating these logs, and then you could have a Kafka stream to which they're pushing to, and you can have one consumer here which consumes from this and push it into the metrics. So usually this would be a consumer group because you want it to scale. You can push it to Elasticsearch. So this is another pipeline that you can form. And this is actually being used in a lot of places. I think one reason, so Kafka was created by LinkedIn, and one reason why they created Kafka was for making it easy to track user activity and events, and analyze them later. So that's why Kafka was created. And yeah, similarly, like for metrics and logs, this is one common pipeline which I think was used. And coming to yeah, and the amount of data which is flowing through these pipelines can be huge. Like it can be in petabytes. Like that's a lot of data. And yeah, so these again, so yeah, so this is like a very this the stream processing is something which is rising and becoming more popular right now. So yeah, that is it about Kafka from my side. So if you have any doubts, you can ask them now. If not, then we will just close the session. I hope you guys, this was something new for you guys and you got to learn. I didn't, this was kind of not organized well, but yeah, I hope you got to learn something. Okay. While storing other messages, no. So in the disk they are not, but over the network they are. You can use TLS to encrypt it over the network when you're sending messages from client to Kafka. On the disk, I'm not really sure. From what I know, I don't think they're encrypted. And if they are, I would say I don't think it's a job of Kafka to encrypt it. You could probably have encrypted disks for this and use that. So like the entire disk itself is encrypted when something is stored on that. Does that answer your question? Okay, I'll take that as a yes. Yeah, if no more questions, you can leave. We're done.